So we'll open the vector one and this Untitled Query one. If you're not up and running with this, that's totally fine. Don't stress. You can go to the website, which I have lost up here. So if we go to the website and we go down here on tutorials, day 2, geospatial fundamentals, the two that we're going to be going through now are this vector one and this dynamic query of snowtail data one. And actually there's a brief introduction here to what we're going to be talking about. So whichever way you prefer, I'm going to go through a fair amount of material here. So if you want to try to follow along and shift enter with me while I'm executing this, you're more than welcome. If you just kind of like to walk through it on the website, the rendered versions of these, that's also fine. I leave it up to you. Okay, if you're having any trouble, either of those is not working, go ahead and reach out to the Hackweek help channel on Slack and someone will help you get to speed. Okay, so I will start. So hi, I'm David. I am an assistant professor at the University of Washington over in the Civil and Environmental Engineering Department. I've been doing a lot of GIS and geospatial work now for almost 20 years, which is kind of crazy. But I now teach these things, which is great. We have a course that we teach here at the University of Washington, and several of us have been involved in previous Hackweek events that are entirely dedicated to geospatial data analysis. So there's way more than we can cover in 45 minutes or however much time we have here. So what we try to do is provide a few examples. I should say Scott Henderson and I have been working on this collaboratively. He's going to lead the Raster portion of the tutorial tomorrow, and we'll both be kind of pinging back and forth. If you have questions, feel free to reach out to us. Yeah, so here we go. So there's too much to cover. We're not going to be able to get to it all today. We're going to go through a few core concepts, and I'm going to try to show some examples to illustrate some things. But you know, if you've taken a GIS class in the past, maybe you'll recognize a few of these things. If not, that's okay. There's plenty of opportunities to learn. And we're going to try and teach you how to do things programmatically with the Jupyter notebooks primarily, rather than the more traditional workflows you may have seen using ArcMap or QGIS or some other kind of GUI-based system. You can do a lot of the same functionality using Python. And the beauty there is a lot of it's reproducible and powerful, flexible, scalable. So that's what we're going to focus on today. All right, so basic concept here, there's two main types of geospatial data: vector data. So these are things like features. It's a set of points, lines, maybe some polygons, maybe it's the snow pit locations. That's what we're going to talk about today. A lot of GIS data comes in this format. Maybe you've used an Esri shapefile in the past. Maybe you've used some other, maybe just a CSV of points with latitudes and longitudes. Those are vector data. Raster data, that's a regular grid. It's like a satellite image or maybe an elevation model. And Scott's going to talk more about that tomorrow. So really, those are the two primary data types. And what we're going to show you with this particular portion of the tutorial, we're not going to be diving into the database, which Mike is going to talk about later. So there will be opportunities to pull material out of the database or pull data sets out of the database. And then you can use some of the techniques we're going to show you here using some tools like Geopandas or Raster, etc. So hopefully it'll start to make sense as you see more of this. All right, so I'm going to hop over to the hub. And I am here, and we've got this vector notebook that is open. So we cut out a lot of material here. So there was more intro I was going to provide, but we're just going to dive right into this. So I'm hoping most of you have seen pandas before or have encountered it. If not, again, that's okay. If you have never used pandas, I really recommend you take, you know, there's actually like a 10 minutes to pandas tutorial or something on them. Let me see if I can find it. Yeah, this one. Pandas is a fantastic package. It's used by millions of people, and it's the core of really the Python data science stack. It's very good at working with tabular data, so rows and columns, kind of like a spreadsheet. It turns out we can use that for geospatial operations as well. So I'm not going to spend much time on pandas, but if you've never encountered it, that's okay. Check it out. It will make your life better. And hopefully you'll see some of the examples. And I don't know if maybe other people can share their how much they love pandas on Slack or later on during breaks. So what we're going to talk about today is Geopandas. So basically, this is it's a kind of value-added version of pandas, or it's a basically it takes all the good things about pandas, all the functionality for a data frame with these other objects, and it allows you to attach geospatial information to them. So these geometry columns. So we can do spatial operations, things like buffering, intersections, spatial joins, things you may have heard about in GIS classes, but have done through some kind of like, menu pull down spatial join, and like some kind of GUI based thing. So you can do the same thing with Geopandas. It also allows you to do analysis, things like reprojection, as well as some pretty nice visualization options. So it's kind of the core vector processing tool. Now, one caveat here, it's not meant for 10 billion points. There are versions under development right now to take what's called another library called Dask, which very efficiently does parallel memory efficient operations, and to adapt Geopandas to do that. But we're not going to get into that. We're going to deal with some relatively small data sets here, which is really 90% of most applications and most of what we're going to do during this hack week. So Geopandas is great. Learn it. There's a lot of under the hood. Just a point here, Geopandas is not, all this is not implemented here. It's using several submodules to handle a lot of the processing. So projections and coordinate systems, that's all done with this PyProj library. Fiona is another one that allows you to open shapefiles or save out a shapefile or a GeoJSON or some other data format. And the Shapely library is what does all those intersections of like figuring out whether a point falls within a polygon or something like that. So there's good information on those. They're a little bit lower level, so we're not going to spend much time on them. But I just want to point that out. Under the hood, we're using several other open source packages from the Python stack. And then under those hoods are compiled, very efficient code. So this is code that was written in C or C++. Maybe you've heard of some of these, but all these a lot of these libraries have been in development since the 1980s. So they're mature, they're fast and performant, and we now have Python wrappers that take this underlying code and make it very easy and accessible. So that's kind of all the intro I'm going to give you, and let's just dive in and start playing with some of this stuff. Okay, so we're going to import, and we're going to import Geopandas, and this is just shorthand. It's just it allows us to avoid typing out Geopandas every time we want to call some function. And then we're going to use this HoloViews plotting package in a couple of cases. Okay, so one of the core data structures for Geopandas, oh, it's moved, is this Geodata Frame thing. So I'm just going to start there. Basically, it's an object. It's a pandas data frame, so can be like a 2D set of rows and columns with attributes. So you can have a record, and then you can have various attributes in different fields. So it basically takes that and it adds a geometry column. Okay, so that geometry column is a special column, and it contains these objects that have the necessary geospatial information for that particular record. So we'll show you what that looks like in a second. The other thing it has is a coordinate reference system, and we'll talk about what that is. That's basically a definition of the coordinate system for those geometry objects, those points or lines or polygons. So those could be latitude and longitude, right? Maybe you've heard of this EPSG 4326 thing. We'll talk about what that is in a second. But basically, it's a data frame that has this, and there's a few other kind of fundamental attributes that are defined that make it a special kind of data frame. All right, so I was just going to call this up. I ended up using the website, but the same documentation string. I don't know if people know about this, but you can always attach a question mark to the end of any object in a notebook, and it will provide information there. So it could be about a function, or in this case, it's a class here. Okay, that's enough. So I'm gonna touch on this because it's one of these things that like you got to go over multiple times. Nobody gets it the first time. Hopefully you'll see it enough. And Micah has actually saved us and done a lot of work to get all of the data sets for SnowEx into one reference system, which makes your lives a lot easier. But basically, these things called CRSs, it's a coordinate reference system. And right off the bat, these can be really confusing, even for seasoned GIS professionals. I still learn new things every time I have to dive into this or teach this. Fortunately, it's been simplified, and there's actually this database, which what this is, it's a set of datum, spatial reference systems, ellipsoids, coordinate transformations, all these things that we need to define where some points are in space, right? So it's not just latitude and longitude on the planet. We could have some projected coordinate system. We could have all kinds of other things that we want to keep a record of. What this group has done is coordinated all of that so you don't have to remember all these details, and made a set of very simple codes to define some common things. For example, this one is a standard latitude and longitude coordinate system. So you don't need to remember all the details of how that's implemented, what the shape of the ellipsoid is, and all these other things. All you need to know is that, oh, my points are latitude and longitude. It's a standard geodetic coordinate system. This is my code. Okay, so most of the data sets you're going to use are going to be 4326. And I'll talk about this one in a second. And if you ever wonder what EPSG stands for, it's the European Petroleum Survey Group. So back in the day, these folks needed a way to reference different projections and define these coordinate systems for data sets that they were exchanging. And this is what they came up with. And now it's become kind of the de facto standard. So plenty of other documentation to read there, but we're going to fly through this. So this one, remember, we're going to talk about Web Mercator in a bit. If you've ever used Google Maps, which I'm sure you have, or any other mapping software, when you pull this up, this is where I am. I'm currently on the East Coast. But if we zoom out, of course, they have implemented some dynamic projection here where now we get a globe. But if we zoom in, eventually we're going to get tiles that are loaded up for the base map here. And as you zoom in, it's loaded in different levels of those base map tiles. All those tiles are stored in this Web Mercator projection, EPSG 3857. So it's great, it's simple, it's easy to go back and forth between points in latitude and longitude to some 2D projected coordinate system. But as you can see, there's a lot of distortion in the polar regions. Greenland is not this big relative to some of the other countries near the equator, or continents near the equator. So it's become the de facto standard for web mapping. People love it, people hate it. It is what it is. But the point is there's a lot of base maps that are in this projection that we're going to use. Okay, and most of what we're going to do during this hack week, we're going to use one of these UTM zones. This is Universal Transverse Mercator. We'll come back to that in a minute. So this is most of what you're going to need to know. You're going to probably have to go between here and here at some point during this hack week. Key takeaways. Make sure your data sets have a CRS defined. Often this is done for you. If you open up a shapefile, you don't have to worry about this. Geopandas will read it and figure it out. Things like ArcGIS and QGIS, so maybe you've done this before. You just pop data sets into a GIS and it automatically plots them on top of each other, right? It's great. It's one of the wonderful things about an interactive GIS. But we have to do that ourselves with some of the Python tools. So we have to make sure that all of our data sets that we're bringing in have a common coordinate system. So we'll talk about how to do that here in a second. Yeah, there's a lot of detail here. I may skip some of this. One note is that all the calculations we're going to do, it's going to be just a 2D Cartesian coordinate system. Basically, it's going to, if we want to know the distance between 2 points, we're going to use the Pythagorean theorem, okay, to figure out that length. We're not going to worry about the shape, the curvature of the Earth. There are ways to do that, but it's much more computationally expensive. So Geopandas and most of these operations are just operating in a planar coordinate system. And yeah, we'll talk about, maybe we'll come back to this. I hope I'm not losing people. Coordinate reference systems, they're important, and there are a handful that you're probably going to encounter. Okay, cool. So let's do this. So we'll start with a quick demo of the projection stuff, and then we'll dive into something that maybe you'll care a little bit more about, the SNOTEL analysis. So let's get some data. There's a number of ways we could do this. We could go to the census, we could find a shapefile, unzip that shapefile, copy the file name into the notebook, and then, oh, wait a minute, I want to do this all programmatically, so it just becomes a problem. So what we're going to do, we're going to use a URL that points directly to a GeoJSON file directly on the web. Okay, so there is someone out there, maybe his name's Eric, but he's staged, or this person has staged files here that are available for the outlying states, counties, etc. And one of these is a GeoJSON. So if we look at that, and I'm just gonna, well, let's see, this should work. It's just a text file. This parses it. So let's just move forward. But basically, this GeoJSON file, it's just a text file, and it has formatted text for each of the records for the US states. And what's great is that Geopandas knows what to do with that. Okay, so we're going to put the URL here. It's a JSON. It's actually a GeoJSON because there's latitude, there's some geometry coordinates attached to it. And we're going to use this Geopandas read file function. We're just going to pass the URL directly to that. So if we go ahead and run that, it takes a second. Okay, that was done. So if I go here and just recall that variable, we see now we're going to get something that looks like a data frame. So again, this is a geodata frame. It's not a pandas data frame, right? So if we look at the type here, we see this is actually a geodata frame. That's because it has this special geometry column. So we've got a record here. This is Alabama. It's got some index over here, an integer index. There's some other attributes here like the area. And then we've got this multi-polygon object, and that looks like maybe a longitude. Here's another one, Alaska, longitudes, Arizona, that looks like a longitude. And note there's multi-polygon and polygon files here, or geometries. We'll talk about that in a second. But point is, we just loaded up this GeoJSON directly from this place on the web. Great, didn't have to do any of that other stuff. Another great function in Geopandas, so this is now the geodata frame, and we're going to call this plot method on that geodata frame object. And what this will do is create a matplotlib figure, and it's going to show all the polygons and the multi-polygons that are in this geodata frame. So that's great. So there's Alaska, there's the continental United States, Hawaii's over here, Puerto Rico's there. And one of the reasons this confused me at first, why we're over here at like, positive 180 is because some of the Aleutian Islands of Alaska actually wrap around here. So there's a handful of Aleutian Islands over here, and that's why the whole display, we get the whole minus 180 to 180, we're crossing the date line. Okay, so let's see what the CRS for this data set is. So we're just going to pull up the attribute here for the geodata frame, and it returns a bunch of text. So we see this is a two-dimensional coordinate system. Hey, look at that. There's our 4326. So this is the WGS 84 geodetic latitude and longitude. It gives you a sense of the extent, tells you what the ellipsoid is. So all this stuff is stored in that record, that EPSG record. You don't have to remember all this. You don't have to type it all in. And what's really cool is that that was defined in the GeoJSON. I didn't have to tell it this. And when Geopandas read that in here, it automatically loaded in that information. So it knows that these polygons are defined, these numbers here, these are latitude and longitude in the WGS 84 system. Cool. All right, so I'm not going to get into too much details on visualization, but there's this HoloViews package, which is an alternative to Matplotlib. It's another way to visualize data. So up here, where did we start? I did this import hvplot.pandas. So basically that opens up the HoloViews backend for pandas, and Geopandas, because it's built on top of pandas, can leverage that. And so what this provides us with is a nice kind of interactive display here for this polygon data set. And if I zoom out over here, so there's the little tip of the Aleutians that I mentioned before that cross the 180-degree longitude date line. So one other quick thing here, there's a lot you can read about hollow views and plotting. There is an option for data sets that are in this WGS84 coordinate system. If you say geo equals true, it'll figure that out and it'll give you nice latitude and longitude axes. Now, one note, this is not a linear, or the units that are displayed on the screen are not necessarily linear, and that's because this is actually on a three-dimensional object, the Earth, and not on a two-dimensional object on your screen. I'm going to avoid going down a rabbit hole there, but just something to be careful of. Okay, so before we're using latitude and longitude, it's great for global analysis and basic visualization, but here's the problem. If you're at the equator, the length of a degree of latitude and the length of a degree of longitude are basically the same. They're not exactly, because it's not a perfect sphere, but they're both about 111 kilometers. As you get farther and farther toward the pole, think about it, the lines of latitude kind of converge to the pole, right? So if you're standing up near, well, you wouldn't stand near the North Pole, we'll do the South Pole. The width of a degree of longitude, if I'm standing at the South Pole, the width of a degree of longitude might be a centimeter, right? If I'm right there, right around me. So it's a problem, and well, how do we get around that? Well, what we can do is we can reproject our data so we have linear units of, say, meters instead of these degrees. And there's a lot here. I'm not going to teach you everything you need to know about map projections. It is a complex topic. It's a fascinating topic. It's really, there's really cool things you can do with this. Just remember, there's no perfect projection. It's up to you to choose a good one. And most of the time, like we said, you can just use a UTM coordinate system if you're at lower latitudes. It's a pretty good compromise for most analyses. Okay, so how do we actually do this reprojection? How do we take this data set in latitude and longitude and turn it into something in meters that we can use to use the Pythagorean theorem to calculate distances or compute the area of a polygon or something like that? Well, fortunately, Geopandas has this 2CRS method, which is the basic way to manage projections. There's also some nice documentation here that you can check out. There's a number of different ways you can define these things. There's our EPSG code. Let's see. Well, let's just keep going. Check this out on your own time. There's basically everything I'm skipping over here should be outlined here. So what we're going to do, we're going to reproject into UTM zone 12 north, which is right on the border of Grand Mesa. So we're going to use that for our example. Turns out that code is EPSG 26912. You may have seen 32612 is another version of UTM 12 north. Just know the 12 at the end here defines the zone. There's different codes for the southern hemisphere of the Earth. But since we're doing SnowEx, as far as I know, SnowEx doesn't have any southern hemisphere campaigns yet, so we're sticking with the north. And if we look at these Mercator zones, so here's the United States. Basically, we're slicing up the planet into 6-degree strips. And we're saying within that 6-degree strip, we're going to define a coordinate system, and we're going to minimize distortion. So we see Grand Mesa is somewhere in here. So we're right on the boundary between zone 12 and zone 13. So for simplicity, we're just going to use 12 for this exercise. One note, I wouldn't want to use zone 12 if I was doing some analysis up here in the Midwest Mountains in Washington. I would want to use zone 10 for that. Because if I tried to use zone 12, I would be going farther and farther away from the center longitude where scales are true and there's limited distortion, and I would get incorrect distances if I tried to use the Pythagorean theorem. Okay, so long story short, let's just check in where we are. We've got our states. These are still in latitude and longitude, WGS84, and we're going to use this 2CRS method with this UTM projection code. And I'm going to store that in a new Geodata Frame. Right, so that was pretty quick. And if we look at that one now, you see it looks the same. right? These are still rows, we still got the same attributes, but now we've got a geometry column and we have some big numbers in here. So those are meters. These are now X and Y coordinates in units of linear meters in that UTM projection. They're pretty big because we're far from the equator. So the Y value is actually, we're going many millions, but we're going many meters away from the equator, which is our 0. Okay, so we'll come back to that in a second, where the origin is. And if we just do a quick check here on the coordinate systems, this is before, this is after the reprojection. You can see now it's been updated. That CRS attribute is updated to 26912. Great. Okay, I think I'm missing a cell here, but let's look at this. So if we plot it up now, so I'm just plotting it up. I'm using an equal aspect ratio here, and I've given it a title. So it's basically the same command as before with hvplot. I'm not doing this geotrue thing, but basically doing this, except with our new reprojected geodata frame here. And I've put a line here for the 0 on the x-axis. All right, we can see on the y-axis we're up at like 4 million meters from the equator, but the origin on the x-axis is somewhere about right here. Okay, so one note, this confused me, and if there's nothing else you remember from this, maybe you'll remember what a false easting is. So let me just show you this. So zone 12 is here. All right, so somewhere over here in what is that, Wyoming? So potentially the western boundary of Wyoming is about the center of zone 12. That's about a minus 111 degrees longitude. So the center of our zone should be somewhere down the middle of Utah, maybe a little bit to the east. If we look at it on here, the 0 on this map is somewhere in the middle of Nevada. So something's not right. Well, if you look into the nitty-gritty details of these UTM projections, they have this thing called false easting. And I went like 10 years without really understanding what this was after learning about GIS. Basically, there's an artificial offset in these coordinate systems so that the 0 is placed far enough away so that there's no negative values inside of that zone, because dealing with negatives is confusing. So if you want to add or subtract numbers, you don't have to mess around with signs. It's always a positive number minus another positive number. Anyway, now you know. If that's, maybe that's just went over your head, but maybe next time you see this term, you'll know what to look for. And just FYI, the true center of the projection is over here. So now I just plotted the line 500 kilometers to the east. There it is. So UTM 12 north, we've reprojected things, and anything along here, along this line, should have true scale. So I should be able to use the Pythagorean theorem, compute an area, measure other things, and I should have uniform linear units of meters in both the X and the Y directions. But the farther I get away from that line out here, I'm going to get more and more distortion, and I wouldn't want to make measurements out there. So it's good for our small little area we're going to be analyzing here down near Grand Mesa. Okay, so we're going to use 12 north. Yeah, so there's some notes here about what we did under the hood. We're using this PyProj library to actually transform each point or each of these polygons from the original latitude and longitude. It's putting it through some matrix to convert those coordinates, those X and Y coordinates, into some other X and Y coordinate system. It's something you've all done. I know you've done coordinate conversions between a Cartesian coordinate system and maybe a polar coordinate system, right? Same idea. There's some function that takes the original X and Y, turns it into a different X and Y. So from latitude and longitude to meters. So you can read about this more. It may seem like this obscure kind of really complex topic, but at the end of the day, you're doing something kind of like this. This is an example. These are polar. You know, there's probably some better examples in here with X and Y coordinates to another one. So that's it. So we're transforming between these two. It's something we do all the time with GIS. So there's complications, and you can leverage 40 plus years of development, so you don't have to write these functions by hand. You can just call to CRS and reproject your data. All right, so it's 2:02. I think I have 15 minutes left, and I will see how far I can get here. And let me check in on the Slack to make sure anybody is, let's see. All right, hopefully people are aware. I see pandas, great. Cool, thank you for helpers, for people who are answering these questions. I will follow up in more detail on these in a moment, but I'm just gonna keep rolling through this. So we're gonna pull up this SnowTel query data set. So let's talk about snow, now that we know what coordinate system we're gonna use. So I'm gonna try to go over some basic concepts, but I'm going to do it using some SnowTel data. So we're going to pull up some points, and then we're going to pull up a time series from a couple of different SnowTel sites. Hopefully you'll get another opportunity to see these transformations, geometry objects, and how to do some analysis of time series. If you don't know about SnowTel, it's great. It's a network of autonomous stations that are out there transmitting data, telemetry data to centralized servers that are being made available within hours to days of collection. So there's some really nice resources. If you've never looked at the NRCS website, there's a really nice interactive viewer here. And I'll just go to snow depth, since I think you can pull out snow water equivalent or snow depth. But I think a lot of what we're going to be talking about for some projects is snow depth. So you can do queries on here. You can download a CSV with a bunch of different variables for different time periods. It's great. So full disclosure, like going on here, doing some query and downloading a CSV, you can just load that pandas and load it that way. Okay, so that a lot of people, maybe many of you have done that. It's pretty easy. What we're going to try and do is do dynamic querying that is fully reproducible. So you don't have to do any clicking or going to a website, or maybe there's a version that changes. Hopefully it should all be reproducible and version controlled here with the code we're going to show you. So this is great. It's great for interactive things. Check it out. There's a lot of information about SnowTel. I don't have time to get into all of it, but maybe you've seen things like this. So this is actually for Paradise up on Mount Rainier, one of the higher stations in Washington State. Snow water equivalent plot. Note they use inches in many of these plots. Maybe something like this, which shows from the start of the water year how the snowpack evolves to the end of that particular water year. And just FYI, you can see somewhere here in late June, when we had the kind of unprecedented heat wave in the Pacific Northwest, the snow melted quite a bit. I think it was melting on the order of 7 inches a day, if I recall correctly. All right, well, let's just keep plowing through this. We're going to use the Kawasi Water One Flow server. So this is not the same as the NRCS, but it's a mirror of the data that are up there. So what we're going to do, we're going to point to this API endpoint. Don't need to worry about this. If you want to read more about it, you can follow these links. FYI, Kawasi is the Consortium of Universities for the Advancement of Hydrologic Science, Incorporated. So it's an organization for advancement of hydrologic science, and they provide services like this API that allows us to do these queries. Okay, and how are we going to get at these? We could do this ourselves by writing some custom requests, but we're going to use some existing package that allows us to quickly query this Kawasi API. Now, it's not in here, but an API is an application programming interface. Basically, it allows you to easily interact with some other software running on a server and dynamically query or request data. All right. So that server is running here, and we're going to use this as the endpoint where we can say, give us SnowTel site X, and it'll return the data for that. Okay, so we're going to install this Olmo thing, and this is a handy little reference here. So this allows you to, in a notebook, pip install. This is quiet, so it's not telling us all the things it's doing, but we're installing directly from a GitHub repository. So that's a handy thing you might want to do if there's something that's maybe not production ready, but you want to bring it in or you want to have others start playing with it, we can do that. So at this point, we shouldn't need to restart. We now have this Elmo package installed, which will allow us to do these queries. Import a bunch of other things. And the first thing we're going to do is we're going to do a spatial query. So we're going to find all the SNOTEL sites using this get sites method, and we're going to pass in that URL. So basically, we're going to use Olmo to run this function, and we're going to say, hit this API endpoint and return it and store it as a Python dictionary is what Olmo will return. All right, so if I just do, see what we got, this is going to print out a lot of stuff. But this is a Python dictionary structure. So here's the key, and then here's the actual contents of that dictionary. And there's actually sub-dictionaries within this high-level dictionary. But this is one site, California. Here's another one. There's another one. So there's a whole bunch of sites that were returned. So that's a little messy. Let's parse that. So this will just get the first one just as a check. And you can see there's the site name and then a bunch of other attributes here, keys within this second dictionary. Aden Mountain, latitude, longitude, other site properties, etc. So let's load that into a pandas data frame. And we're going to get rid of any empty records here. Fortunately, again, pandas just saves the day. We have this Python dictionary. Now we have this beautiful 2D table with an index for each of the SNOTEL sites. Great, so we could do something with that, but we're actually going to parse out these latitude and longitude values. And don't worry about this too much. Basically, I'm going to pull out each of these dictionaries for each record and then create a point object for the latitude and longitude values and store that in a new column called geometry. Maybe you can see where this is going. We're going to take that geometry column and eventually create a geodata frame. So let's just look at what we got here. So we've got SNOTEL index, got some code, some name, something about the network. Here's an elevation value, some other information about the county, etc. And now we have this geometry column, and each record has this point geometry. So before we had polygons and multi-polygons. Now we have this point, which is just a single X and Y coordinate versus a series of X and Y coordinates that are used to define a polygon. And you can see, guess what coordinate system we've got here? This looks like -120, 41, -112. That sure looks like latitude and longitude. So this is EPSG 4326. All right. So this data frame at this point doesn't know that. It's going to tell me some kind of problem here because a data frame doesn't know what its CRS is. We haven't created a geodata frame yet. All right. So let's make a geodata frame. So we've got this geometry column. All we need to do is say, hey, those points that we were looking at before, those points are latitudes and longitudes. And here's how you can take those and figure out how they should be referenced Geopandas. So we do that. And it looks the same, but now we should have a coordinate system defined for this geodata frame. And if we just look at this real quick, there's 930 records. So it returned a point for 930 of the active SNOTEL sites, or at least where there's a record of a SNOTEL site. They may not all be currently active. Okay, so let's quickly plot them up. We're going to bring in our states again, just because I really like using that one. So, and we're going to plot them up. So we're going to use the geodata frame, and we're going to use the plot command. So this is a matplotlib plotting function under the hood. And we're good. There's a bunch of other stuff here. This is just for visualization. There's not a whole lot going on here, but I'm going to say, I'm going to color the points based on the elevation values here. So it's just another way to visualize things. And then I'm going to plot the states on top of there on the same set of axes so that both the points and the states will be rendered. So we're combining point data, and both of these at this point have the same coordinate system, which is good, which means that I can put them on the same axes, same coordinate axes, and they plot where they should. If one of these was incorrect, it had a different projection, and I tried to do this, it wouldn't work. The points would be floating off somewhere in space. or maybe very close to 0, 0. That's often what you'll find. If you do a plot like this and you get one data set but not the other, go zoom in if you can down near 0, 0, and your points might be hiding in there. And it's probably an issue where you've got big meter, millions of meters in that UTM coordinate system. And then you've got like 40 minus 120 in decimal degrees. And so it's you're mixing units, and it really doesn't know what to do with that. Okay, so as you can see here, there's a bunch of stations up in Alaska. So sorry, Shad, and all the other Alaska folks. Well, no, Shad, sorry. Whoever's here from Alaska, I apologize. We're gonna throw out all your SNOTEL sites, and we're gonna limit to just the CONUS sites. So we're gonna basically say any name in our database here that has Alaska in it, we're gonna toss it out. All right, so it's just a simple filter, and we're gonna create a new geodata frame. Now, when we look at that, we see we end up with 865, whereas before we had 930. So we've tossed out a chunk of our points. And we'll just do a sanity check here. There we go. Okay, so now we've just got the sites here in CONUS. Note we're missing a bunch in California. It's a different network. They're not part of SNOTEL, but really nice representation for mountainous areas across the Western US. So thank the USDA and NRCS for providing this amazing data set. Okay, one note, say we want to save these points. So we want to load them up in QGIS, or we want to load them in some other notebook. Geopandas has a really nice to-file function. So remember before we read a file when we loaded in those the states, we use the Geopandas read file. So that would load up some JSON or shapefile or whatever. Now we're going to save it out. So we're going to do, from the geodata frame, we're going to save it out to a file. We could do an Esri shapefile. We could do a GeoJSON, doesn't matter. There's a number of different options. And in this case, we're going to save it out. I'm going to use a GeoJSON. So if I run this block, it should create a new SNOTEL CONUS sites GeoJSON. And if we open that up, on the hub here, we'll see that there's a lot here, but here we go. So now this is an external file that's been written to the disk that is really just a text file. If I just say more SNOTEL JSON, you can see, here we go. We're back in this kind of structured JSON format, but within here is embedded all that information that we were looking at in the geodata frame, including the point coordinates that we had stored before. And yeah, so we'll leave it at that. Coordinate systems defined. So I should be able to, at this point, if I wanted to, I could say geopandas.read file. And it's going to load it up. In this case, I didn't save it to a variable, but it just read that file directly from disk. And here we go. I'm ready to roll. Okay. So I'm running short on time. I'm going to see how quickly I can go through the rest of this. If not, you can try to go through this on your own. But we're going to do a couple things. We're going to figure out which of those points is at Grand Mesa. So to start, I've defined just a polygon here. I'm going to skip this geometry section just in the interest of time. If you're curious about what these geometries are, look through this section. There's also some good tutorials, but let's just kind of roll through this. If you need to get at the points in the geometry, here's how you can do it. What we're going to do, we're going to do a search. We're going to search for all the SNOTEL sites that intersect this polygon that defines Grand Mesa. So we're going to create a Boolean index. So here we have a record for each of the sites in the geodata frame, and most of them are false because most of them don't actually intersect Grand Mesa. They're off in Montana or Washington or wherever. Look at it, there's actually only 2 that actually intersect our Grand Mesa polygon. So let's get them. Let's figure out which ones they are. So we do that, and here I'm just isolating those 2 sites. And we see these 2 here. So index 622 and 688. Maybe some of you know these names, Mesa Lakes and Park Reservoir, and there's their coordinates. Plot them up. Okay, That's not very useful, but there they are. So let's get some context here. We're going to use some of these tiles, and we're going to use some of the hollow views plotting. So this is the query that I did. There's the 2 points that were returned. And when we look here, we can define this hover function, which will tell us the name of the index, etc. So it makes it easier to like find points interactively. And here, let's add a base map. So we're going to load in these web Mercator tiles. Again, they're this 3857 thing. And we can plot up the same plot with a base map. And we can interactively zoom in here, and it'll page in the necessary tiles in the base map to give you the more detailed satellite imagery. And this is the Esri base map that's been prepared. And actually, one caveat, the SNOTEL sites are actually not exactly where they say they are. If you've ever run into this before, it's done to avoid vandalism. But so I think it's probably within 100 meters or a few hundred meters. If anybody knows, maybe you can type that in the chat. But I don't think this is, maybe someone can take a screenshot and share it if they can find it on this base map where the SNOTEL sites are on Grand Mesa. That might be kind of cool. Okay, so we know where they are. The other one's over here, over at Park Reservoir, kind of on the eastern side of the mesa. And I'm over time. How are people doing?
I think we have a break planned for until 11:30. So if I may suggest that we maybe give everybody like a room to breathe and come back, or maybe follow up on this tomorrow or so.
What do you want to do, Scott?
Yeah, I think it's a good time for a break for folks. So David,
okay.
If you just go over the last things after the break, you could do that, or I could cover the last bit of it tomorrow.
Okay. How about I give people a 1-minute overview of what's coming, and then if people need this for their project today, they can jump ahead. Otherwise, we'll talk about it later.
Okay.
So, okay, cool. So here we go. We figured out our sites. Let's actually get the data. We got latitude and longitude. That doesn't matter that much. This will query to actually get the records for snow depth. You can modify these, and note there's dozens of variables here. So if you're looking for metadata, there's temperature, average temperature, daily, hourly, monthly. There's precip. I'm not sure how much you talk to people about how much to trust that. But there's a lot of variables that are available here. All right, so basically what we're going to do is grab those, create a new data frame, and we'll have nice time series of snow depth for this site over the last 20 or so year, or snow water equivalent for the last 40 years. So if that sounds useful, and basically you can pull out a single day for some satellite observation, or maybe where you've got a LiDAR observation and you have a SNOTEL record of what the snow depth was at those two sites. So it's a nice opportunity to do comparisons across time series, as well as more climatological analysis for longer term studies. And I think that's more or less it. So thanks for sticking with me. I know that's a lot of information. I tend to overload people and put it there so you've seen it. You're not going to remember all this stuff, but you can go through it later on. You can, on your own time, if you're on your project, you need to do some, I need to do some kind of spatial intersection. How do I do that? You know where to look, or you can ping me on Slack. I'm happy to answer questions or help you get through stuff. So with that, thanks for sticking it out, and let's take a much needed break.